or I'm not saying lab. Sometimes there is more. If the lab is running a lot, then sometimes it is not. But in the beginning, lab itself could be a huge taxing, demanding course actually. So I don't know. And even like, why should the lab be stationary? You have to think about labs, right? All those arguments comes in.
I would say that what you're saying, your wife would have had a lot of the same experiences and opinions.
Yeah, so yeah, exactly. So I think, yeah, all this. Yeah, I don't know. First of all, I try to stay away from all this. And second thing, even if I'm given the power or something, I don't want to do these things. It's a little, yeah, I don't know. I think you get the point.
I was telling somebody the other day, I said, it was a student was complaining about something, and I said, well, I'm just a grant assistant here. I said, so I get to pass on problems to somebody else. Unfortunately, where I work,
Yeah.
I don't get to do that.
Yeah. Sometimes there are
The anonymity of a grad student is a nice thing.
Yeah, I agreed. Yeah, hopefully we can all meet.
Now, did your wife get vaccinated as well?
Yeah.
So everyone in our family who could is. My daughter is not quite until they lower the age.
Yeah, so let's plan that. Yeah, I think that will be nice. Yeah, after year week, because she also finishes it. I'm sure.
It's nice to get together with her family because everybody in her family, well, my family too. So
yeah, sure.
They've been vaccinated because of their jobs.
Yeah.
And so
we are okay. As far as everyone is fine, then it's okay. Anyone is even a little sensitive, and we try to stay. I think that's the main thing. Many are, even if you're vaccinated, many are just sensitive, and which is understandable for some people.
I know that Shari is, I haven't asked her if she got vaccinated because
yes, she is. Yeah.
So she has talked about I think Hansika.
Hansika, yeah, that's not her. You mean her daughter? That's her student.
Her former student. We're kind of all collaborating on something.
Okay, cool.
And she's talked about doing social get together.
Okay, yeah.
Because I'm actually closer
to Hansika.
Than
I see.
Because she's in Indianapolis.
That's correct. Okay, yeah.
I actually saw her defense and didn't know her at the time, but I was invited to observe because I was working that summer with the Shari, and when she came in on the work we were doing, it's like, wait a minute, I've seen your defense.
Yeah, let's talk about it. Yes, where did Moses run away?
I think he went to get some water.
Yes, he always does. Okay.
I started on my second 32-ounce tumbler of water today. Well, now that it's getting hotter and muggier in here, it's
good. Yeah. Okay, we have the last day of the lecture in this course. Hopefully, I can finish what I want to.
And everyone's late.
Everyone is late. Alia said that she won't be able to make it. Her daughter is sick, and they have to go take her. Yeah, so she's worried that she has this flu symptoms. So they're going to have this test. So that might be stressful. Hopefully, all works out fine. She wrote separately. So who else? Oh, Michael. Michael didn't come last time either. So yeah, hopefully.
We saw him later.
Yeah, I think he tries to attend it later, probably. I don't know what, because last time also he was not here, but then he was having the office hours. So probably once you have online things, people I think can take advantage of that if they want to. Okay, so now Moses. So no homework remaining, that's a final exam. This is the only thing remaining. Remember, all the homeworks, everything should be in by tomorrow, basically, right? Tomorrow night. Moses is looking at.
I was thinking sometime during finals week, but tomorrow's okay.
No, let's get this done. This will never get over.
Well, I mean,
that's fine.
okay.
There's Michael.
Oh, okay, cool.
The problem, the 10th homework, it doesn't look horrible. It's just gonna be.
10th is the last one?
The last.
Yeah, just keep going. It's like we're going through a chapter and yeah, I've made it.
Keep track of what your things and it works out okay.
Yeah, is that useful? Does it come out useful that way also? Like sometimes the complaint is that, okay, then students are not thinking too much, right? It's not too challenging. It's just doing the simple algebra in between. But I feel that's also useful. Yeah.
I've actually thought about doing that for my students,
Okay.
giving them a problem where I do that for them and then letting them kind of approach something a little different on their own.
And different on their own also, right?
I think it's a good teaching tool.
Yeah, okay. Good.
I like it too. I mean, I usually don't see how it all fits together until I finish the problem. Like sometimes it's not clear like why we're doing some of the middle steps, but I like that it comes together, which is
At the
nice.
end, okay. Maybe that's the point I have heard complaints about. Why are we like each step? Sometimes it's not motivating enough, especially for undergrads. Or first time I did this was when I was a grad student. I was TAing for someone, and we have these tutorials. I think we don't have it in this department, but sometimes for physics introductory course you have a tutorial associated with it. And I was making the problems for that, so I did exactly what you're saying, break it into many things, and they have about 30 to 50 minutes to work on it in groups. And everyone used to ask, why are we doing this? This is too trivial. Like each step is trivial and they don't see the end of it, right? So I think, and probably undergraduates are not very motivated to think about the whole thing. I felt a little, that was a setback. First time I was implementing it and I felt it didn't go that well. But in graduate level, I still I think I like it, but I don't know. So any feedback is good. So whatever you said was useful.
I think sometimes like getting solutions is helpful because sometimes
again, Jordan?
I think sometimes getting solutions is helpful.
Yeah.
Providing maybe even if it's not like the solutions to all of the problems that you give, but just some maybe the ones that where you're trying to get us to think, and if you finally answer the question correctly, it doesn't necessarily mean that you've really thought through all, because sometimes your problems are where you're going because you say, show me that this is what it is based on some method.
Got it.
You may achieve the correct result, but not really
The right approach that I might have intended.
not the approach that you're looking for.
Got it. Yeah. So solutions helps. Yeah. I agree. It's just a little taxing. And in fact, I think I like the solution part in the sense in the introductory physics course, at least during this year, what I have done is that I give them the solution before it is due. So I basically make a video of solutions and I post it about 24 hours back and I tell them. So they basically, if there will be about at least, I'm sure 40% of the students who don't do anything until the end and then just look at the solution and do it. But that's their responsibility. I don't care. But I see that many people work on it before. Like there are at least 25% of the students who work on it before and then wait for the solutions, check it, and then submit it. So yeah, as far as the grades go, it is tested on the midterm alone then. This is almost full points for everyone. And surprisingly, even then about 10% students lose it. But most of them get 100%. And then it's just that it's free points. I don't mind. As far as you make the midterm harder, it comes out the same. So I've tried this, so we'll see.
Like for instance, right now I'm doing homework 8, 9, and 10, and I'm
Mhm.
like 90 point something% done with all of them, with each one individually. But there's certain portions of each one
Struggling.
where I'm just, I think I'm headed in the right direction, but I may end up spending like 2 hours on a problem that maybe just one little hint, you know.
Those are the places where really, if it was not a pandemic time, the office hours really would have helped. You come into my office hours for even 5 minutes. I mean, half of your questions, or most of your questions will be immediately answered. But it's, and I still have office hours, but somehow it is not very popular. I think I have very few who come to the office hours. Yeah. But yeah, feel free to ask me, but otherwise, yeah, it's the end of the semester, so one day is done. Do submit it, even if it is 90% done, submit it. Okay? Like some submission is way better than no submission. Okay, let's get going. 10:15 to 12. And this is in class, remember? It's possible that we might be more than what we are here, like more than what we are, I mean, even including, there might be an extra student or something who might be taking the exam. So, so we'll see. Be ready to volunteer to, maybe a couple of them can go to the students' launch or something. Maybe among you three, right? Someone. Like be prepared for that. We might be, already we are 7, I think, including me. So we might be 8. There might be more.
Are there like undergraduates?
No, it won't be undergraduate. Like there are people who have not completed the course before. So they might be here. So they're still, is that clear? Yeah. So I don't know, it may not happen, but it all depends on students. Come on. Okay. So in that case, just volunteer at that time. That's okay. So we talked about radiation, and mostly we worked in the time and space domain. So we basically talked about angular distribution of radiation. Like if something is radiating, that means any accelerating charge or current distribution radiate. And first of all, in the far field regime, we're talking about like we said, the dome of our universe. We are observing it there, and we were mostly interested in at what angle, how much radiation is there, 90-degree angle, 0-degree angle. But often, especially if you're working with cell phone and all, you're also interested in what the frequency dependence, how much certain frequencies tend to go in particular angles in a particular way. And so we want to take interest in frequency dependence, and frequency dependence is basically the Fourier transform of time. So Fourier transform of the final expression that we have is all that you need. That's good enough. But it's often easier to go back, all the way back in the first step and do the Fourier transform and then follow the steps again. So what we're going to do is go back to the very first step with that radiation, redo the whole calculation, get the frequency distribution, and hopefully with all this time remaining, we'll talk about a particle going faster than speed of light in the medium, right? And how it will look like. That's what is called Cherenkov radiation, and we will get the relation further. So let's call this the spectral distribution for now. Spectral distribution. Radiation. So remember how we worked on it. So we said scalar potential. began with the scalar potential, then we dropped all the 1 over r square term and got the leading contribution. Let's do it in time first. And in time, this is 1 over 4 pi epsilon naught. That is, you integrate not just on all the sources, but all the instances where the source is moving. And at every instant in time, it's also getting contribution. This is all space. And the Green's function was retarded. It takes care of the retardation, and that is, what is this? And that's r minus r prime over c. And this is charge density. Just for completeness, let me write the vector for magnetic vector potential also. Pretty much identical. E naught over 4 pi prime q or prime. Check. It out. So that's our beginning point, and let's give a wanting to Fourier transform this. And if we are only interested in Fourier transforming the time, this will be phi of r omega will be equal to the integrate over all time. So that's with a frequency. If you want components of the Fourier in the Fourier space, and phi of RT. That's how you go into frequency domain. We have used this sufficiently, so I don't have to elaborate on that. Often we will want to go even the position we would like to go into the wavelength regime or wave number, we call it. So let's say if you further want to go into K, okay, so this is the Fourier component of space, then you would say this is minus infinity to plus infinity K. This is dqr, and this is all space now, and this is minus ik dot with r plus I P. One might wonder why is there a minus sign for space pieces and why is there a plus sign for the time, and why is that? Is that relevant? Why is this positive and why is this negative? Same Fourier transform. Does it matter? It does not matter. Usually I can put a minus sign and that's also a Fourier transform. Basically you can change it. I can always substitute t is equal to minus t and you can switch over it. It doesn't really matter. But once you choose your convention, it is usually for time you keep a positive and the space you keep a negative. So that whatever is sitting here is Lorentz invariant by construction. Right? K dotted with omega, sorry, K dotted with r minus omega t is Lorentz invariant just by construction. So it's just like everyone keeps that, but plus or minus might change. Okay, and same thing works with vector potential also. Okay, so let's start with this here, and let's substitute this in here, do the time integral, and let's see how that goes. So that's what we want to do. So phi of r, should I do both together or no, phi of r omega? So this phi of r omega is equal to 1 over 4 pi epsilon naught there's only time that is coming in. And this is dt minus infinity plus infinity e raised to I omega t times and rho of r prime t prime. In the almost gone. Sorry for that. Okay. The only place where the time t shows up is this delta function. Let's evaluate that. So all the t equal to that goes into the numerator, but then we have to be careful that to move this exponentially inside here because this has t prime dependence. So I'll bring it in. So that's equal to 1 over 4 pi epsilon naught minus infinity plus infinity dt prime d cube prime exponential of t gets replaced with t prime, so that's I omega times t prime, and then there is I omega times r minus r prime over c divided by r minus r prime. It is actually so this. Can I do this in one step? I think so, but okay, let me clarify. Confused. So rearranging these integrals, all this is r dependent. Move it to the left. Exponential of I omega over c times r minus r prime divided by r minus r prime. Right, and the time integral moves to the front, basically separating the integrals. dt prime e raised to I omega t prime rho of r prime times t prime. And what is this? If you notice, this is exactly this, right? Here, except that this is a different function. So this is the Fourier transform of the charge density. So Fourier transform of the scalar potential is having this as your potential, and instead of time dependence, you work with the Fourier transform here, which is rho of r prime omega. So often you will, so in other contexts, you will say that this is the Green's function, which is frequency dependent. Typically, we earlier, this is the time dependent Green's function. If you were to Fourier transform this, you get this. So this whole piece is a Fourier transform of your complete Green's function, which have the delta function over r minus r prime. But let's not explore that here. That's just a passing comment. So once we have this, now we have our, oops, I think I removed my camera. So my radiation field, frequency dependent radiation potential, actually scalar potential, is dq r prime e raised to I omega over c r minus r prime divided by r minus r prime. And often there are lots of problems you can build out of this. and this is an immediate generalization, right? 1 over r times statics, a better generalization from statics, where the frequency dependence shows up more plainly. But we are interested in radiation. In radiation, things are much simpler than to in far field problems. We say r minus r prime is equal to r minus r hat dotted with r prime vector, right? That's the approximation. I shouldn't say equal. This is approximation. When you're very far, that's what it is. And that's in the numerator, that's in the exponential specific. Oops, this is magnitude. And when it comes to the denominator, it is sufficient to put just out. Right? We have shown that in other places, so the same idea works in here. So this is equal to 1 over 4 pi epsilon naught. 1 over r comes out of the integral. Right. And this is e cube of prime exponential of I omega over c times r minus r hat dotted with r prime and rho. Okay. So this can be, that is this first, there are exponential, there are two pieces in this, in the argument. First one is independent of r prime. Let me capture that. This is e raised to I omega over c times r over r, an oscillatory piece. And the remaining is exponential of minus I omega over c r hat dotted with r prime times rho and that seems to be very similar. If you look up your Fourier transform in the position to wave number region, that's very similar to Fourier transform. So let's write it in that form. Let's say, let's define a vector k, even though this is like a wave number. So whenever you think about wavelength, like we say position and or frequency, and then when we talk about wavelength, you ask what is wave number, what is the direction associated with the wave number, and it's a direction of propagation. Here we are observing, so the radiation happens in all directions. So we are observing it in an observation, in a direction, angular direction, and that's what the direction we'll associate. Okay, that's a definition of this. Omega over c plus r hat. Doesn't happen, like radiation is happening in all directions, so there is no propagation in that sense. But let's define this to be k. And its magnitude is, of course, k is equal to omega over c. So that's our, the physical interpretation is, this is not physical, it's just a convenient parameter for us. It's not really coming out in the box. So this is equal to, then, in that language, 1 over 4 pi epsilon, e raised to I kr over r. And this now can be written as e cube r prime. Am I still in the board space? Yes. And e raised to minus I vector k dotted with r prime and rho of r prime omega. So this is that's a Fourier transform of the charge density. And that's very convenient then. We are saying scalar potential is the frequency dependent part of scalar potential is having no integrals, it's exact. Once you know the Fourier transform of your charge density. And this is the principle you use, and this will be the same thing that will happen everywhere. Scalar potential will behave like this, vector potential, electric field, magnetic field, everything will be exact. There will be no integrals, no work to be necessary. But you have to calculate the Fourier transform. And this is what you see in X. You might have heard that when you're doing X-ray, what the X-ray picture shows you is actually the Fourier transform of whatever you keep. Have you heard this before? Like, especially when you do DNA. Like, this was a big challenge. They saw the X-ray of the DNA molecule, and it was very hard to interpret what is going on. So basically, they had to do this Fourier transform that was not obvious, and there were challenges in that. But whatever you see in, like a crystal is, think of a crystal, there are lattice that builds the crystal. So at each point of the lattice, there are atoms sitting. And now think of Fourier transforming those points. The discrete objects go to the Fourier space in the K space, which is called the reciprocal lattice. The X-ray actually sees those points in the reciprocal lattice. So you'll always work in that. So crystallography is all about translating from one to the other. And I think that we also have a course here which actually emphasizes a lot of that. Shari teaches that. And pretty nice, but all based on this idea that Fourier transform. Once you have the Fourier transform, basically you have the scalar potential, electric field, everything depends on that. It has that same properties. Okay, so that's your scalar potential. Same thing goes through for vector potential. We don't have to do it again, so it's almost immediate. That's R omega is equal to mu naught over 4 pi times e raised to I k r over r times j. Current density. That's all. Okay. So that's, yes.
So this is general for all radiation in the far field limit?
In the far field limit. You have asked me this before. I'm purposely trying to. Okay, so here is my best answer for this. A far field approximation also involves non-relativistic. If the particles are moving with relatively slow, by particles I mean there are this current and charges that are moving around that are accelerating, especially when you're doing antenna problems. This is all good enough. But sometimes particles are going very fast, like for example in the CERN lab or synchrotron radiation, then they're going very fast, and then the far field approximation is not sufficient. So far field approximation is not just far field, so that's a good way of capturing it, but you have put restrictions inside it. And the point is that say far field has this R prime in it, which is an integral parameter. What do you mean by an approximation that has an integral parameter? Integral parameter is meaningless, right? Unless you talk about the confining region.
What do you mean by an integral?
So for example, so when I say that,
it gets integrated out.
yeah, dx prime, right? When I say dx prime of f of x prime, it goes from minus infinity to plus infinity. X prime has no physics in that, right? Minus infinity to plus infinity. Okay, so you cannot say that, oh, if x is greater than x prime, that's meaningless. That I say meaningless and then I've done it, right? So that's a way of motive. But what is happening here is that x prime usually is confined in a region, right? And like that's a source there somewhere, right? That's an atom. So there is a scale of the atom coming into picture, which doesn't come in unless you specify the problem. So since we are making a formalism, it's okay, but there is a catch in there. And so usually, so in scattering, there is what is called scattering length, which is specifying this radius. So it has to come natural. You cannot say that, oh, this is going to be, oh, there is the size of the atom there that's coming into picture. So it has to come naturally, and it becomes challenging as to how you define it. So it's called the scattering length. There are ways to do that. But for now, the simple answer I have for you is that far field approximation does not mean that you captured everything. If you're non-relativistic particles, then you're good, then you're reasonably good. But if you're relativistic, then you have to go further. Then you have to keep constant. So that's the best.
But our result does cover relativistic particles as well?
No, this is non-relativistic, let us say. So since I am in far field, you should be careful. So if you, for example, if you want to do synchrotron radiation, that is not a good idea. But if you're doing antenna problems where there's current charges moving around, you're good. Okay, so that's the two distinctions I can make.
Okay, thank you.
So yeah. Or be critical. That's the best way to say. So here, antenna problems are good, but not too fast. Okay, so that's your potentials, and let's see. So from this point, we can calculate electric field, right? Let me write it here so that I can try to do it here. Right? So the electric field or magnetic field is equal to, is this visible there? Yes, magnetic field is del crossed with A, and electric field is negative gradient of phi minus dA by dt. The moment I decide to take a gradient, I have to decide which are the R's that I can hit. I can hit this R, I can hit that R. There are only two places. Earlier when we were doing time dependent, in the time domain there were three places you could hit. So now it's slightly easier if it's two places. And when it hits this R in the denominator, it immediately makes it 1 over R squared. But radiation is 1 over R dependent, right? That's what we're talking about. We're dropping that. So we can forget about hitting this. It hits only here. When it hits here, what does this do? Let's evaluate that for once, and then I'll erase this here. So gradient.
So I have a quick question. Don't you
Yes,
miss out on that unit vector then? Like a direction? Like you would have R hat over R squared?
We will see it. Let's see. So give me a minute and then ask me again. Okay, so this is e raised to IKR, right? So I'll pretend as if I'm doing normal differentiation. So it brings down and it gives me back e raised to IKR. And then I have to hit this R, so it is IK times gradient of R, right? But gradient of the magnitude of R is R hat. And that's what probably you're saying. So this is IK times R hat. Is that what you're pointing out?
No, I was pointing out that if you ignore that R in the denominator, you're going to miss out on another R hat value, would you not?
That's correct. So for example, when I do this exponential, I get R hat. If I hit on the 1 over R, I get minus R hat over R squared, right? Because this is the potential that's electric field, right? So this is also contributing, that's also contributing. But since there is already a 1 over R there, this becomes 1 over R squared. In radiation, I want the dominant contribution. In fact, that's more than that. And on the dome, it cannot survive that part. This can survive because the flux has another R squared. When you do this, what do you call angular integration, the area of the dome itself is having an R squared. So when you have a product of two quantities, this contributes. This is not killing. This will really kill. Like by the time you reach the edge of the universe, this will kill it completely. Is that clear?
Yeah, that makes sense. Yeah, you just want the dominant term.
Dominant. And in fact, it is actually no R dependence in the power. Okay. So because of that, so basically I have to do wherever I want a gradient, I have to, and notice K times R hat is just vector K itself. right? So this is equal to I times K, remember your definition of K, times e raised to IKR. So wherever I see an IKR, or wherever I see a gradient, provide an I times K, that's all I have to do. Okay, so that's going to be my prescription to go from here to there. In fact, I'll do one more, that is time dependence also we are worried, right? So, time dependence requires more work, right? And the static, okay? Time dependence similarly, okay, involves going to minus I omega. It's not very obvious here, you have to go a few steps back, right? You have to go steps back, and wherever you have an omega, so wherever the time dependence comes in, it will bring down an I omega. And that's true in any Fourier transform in general. But this is a little trickier because this is an approximate, right? There's a hat in it. So this is not a standard Fourier transform trick, but yeah, since it works in the standard way, it will work. Okay, so that in that way, let me write down my electric and magnetic field immediately. So this is going to be magnetic field. It's going to be equal to I said IK, right? So this is IK. I'll write it as I omega over C times R hat crossed with A of R omega. Right. And I want to write it in the following. I want to write a minus R hat. Remember, we had the similar expression, just match it. This is d of R omega. Crossed with as mu naught over 4 pi. I put in a mu naught over C over 4 pi. Okay. And so I've added a C there. 1 over R I capture out. And then this is what we call it the effective current, right? So effective current is going to be e raised to IKR. Then I have I times omega. It's I times, but there's a minus sign there, so it's minus I omega over C times J. Okay. And there was a C I added, so this is C. Okay. I kind of have done this in 3-4 steps, but I kind of wrote it down. But it's hopefully. If you remember your effective current in the time domain, the only thing that has happened is that this would have been an integral there. This would have been a time dependent quantity, and there would have been a derivative with time. So derivative with time got minus I omega, and before you transformed everything, and there is this e raised to IKR remaining. Hopefully that's the extra piece that is true. So mostly the same. So let me and electric field. Yeah, so since this is the last one, so let's to catch up time. Let me say that one can show quiz, right? Yeah. The last quiz. Okay. So show that this goes through exactly the same way as we did in the time domain, but this can be shown to be minus R hat crossed with C times P. So basically evaluate these quantities and put it together, and there is a cross of a cross product that shows up. Okay, so we are there. Almost there. No, there's still more work to do. So again, writing this down, C times the magnetic field is equal to minus r hat. Yep. Sorry. Yeah, let's write it like this. Minus r hat crossed with mu naught c over 4 pi 1 over r. And we have this is I now, the effective current, iota, not the I. And now this does not depend on space and time. Instead, it depends only on angles earlier also. And now it was T minus R over C, but now this is omega. That's the difference. Earlier it used to be T minus R over C. The effective current, which is having only angle theta phi, is equal to just this would be the e raised to I k r minus I k, omega over say remember is k, right? Times j of k omega. That's it. Okay, so Fourier, if you know the Fourier transform of your current, then you know the radiation pattern. That's a simple idea of antenna. As if you know the Fourier transform of your current distribution, that's how your radiation will look like. Okay, we are though interested in power. dE power is energy per unit time per unit angle. Right? So power per unit solid angle we showed was equal to this comes out to be r square times r hat. That's your area integral, right? R square times solid angle is your area times r hat dotted with E crossed with H. That's your, and all this in position space. I should clarify that. Crossed with H. And H is, if you want to write it in terms of B, then you would say this is B over mu. That's R square over mu now. Change your cross and dot, right? And this becomes C times D. So this is R square over mu naught times R hat crossed with E C times D or T. Put in another C, so that you divide that out, and that's your square. This is also equal to, we have done this in other ways, and this is also equal to 1 over 4 pi, basically adding and subtracting or providing these coefficients here and there. This comes out to be mu naught, so that's your resistance, right? And times C times D of RT over mu naught C over 4 pi times 1 over R. And it is nice to write it like this because then you see that all those coefficients sitting in the magnetic field go away. And this is also equal to, I can squeeze this in here, 1 over 4 pi times mu naught C over 4 pi times R hat crossed with effective current square. Did I fit it in? Yeah. But we want to concentrate on this form for now, for a moment, and then we will go to this form. Okay. So that's just for your reminder that this was your power. We want the frequency dependence, so let's actually integrate with time. So this is, now this becomes energy per unit solid angle, and let me keep this as it is. And now I have a time integral, dt, minus infinity to plus infinity. And there are two magnetic fields, each one I am going to Fourier transform. So this this is d omega over 2 pi e raised to minus I omega, only in the time domain, or am I doing it in the frequency, or yeah, just the time. E raised to omega t times CB or omega. But now remember, quantities that are real in real space or the physical space can get complex in the Fourier space. So in the frequency domain, the magnetic field can be complex. And there is another piece here dotted with. Now, this is a new integral, so I put a prime there, divided by 2 pi minus infinity to plus infinity e raised to minus I omega prime t. Okay. Any questions there? I just Fourier transform each of this magnetic field. These are two real quantities. It doesn't matter what it is, but since they're real, why not write it as a complex? Real is real, so complex conjugation is very good quantity. But that just gives some symmetry and things get easier to deal with. So not easier, just the pattern. Okay. Okay, so let's evaluate this. The time integral is doable in that because they are just exponentials, right? So that's equal to, right, this is d omega over 2 pi d omega prime over 2 pi c times d or omega star dotted with c times d or omega prime. And the integral in time is minus infinity to plus infinity dt exponential of, this becomes a star, so that's I t omega minus omega prime. The integral in time is, what is that equal to? We used this before.
2 pi times the delta function.
Good, very good, right? So this is just 2 pi times delta function of omega minus omega prime. And the moment I identify that, one of the omega prime integrals can be evaluated because that's just lets omega equal to omega prime. So what that means is that this whole integral is just r squared over mu naught mc d omega over 2 pi, and all the frequencies are identical, evaluated. But now we have to keep the complex conjugation that has meaning in this. Or let me write this. At this stage, if I want to define my frequency dependence, so here's my, so energy per unit frequency, per unit solid angle is equal to r square over mu naught c, and that is this extra 2 pi. Remember, this is minus infinity to plus infinity. So frequency usually doubles, right? Frequency of plus and minus is the same, so it's a double counting there. But either you make it 0 to infinity and give a factor of 2, or we are actually saying, so 2 pi reminds us that we are actually going in that whole minus infinity to plus infinity. Usually the frequency dependence is squared frequency given, but not necessarily, actually, not always necessarily. Actually, today we will see a linear frequency dependence, but that frequency always should be positive. Or the way to put it is, in Fourier transformation, sine omega t and sine of minus omega t, they are not independent functions. Sine of omega t is exactly the same as sine of minus omega t, except for a minus. So these are not independent special functions, so they are not really independent. So if you get two of them, it's good to say 0 to infinity. That's the way to put it. Okay. Hopefully, there is no confusion. Okay. Any concerns about that? Okay, so So the point is, I just do frequency dependent magnetic field and squares, right? That's my very similar to what we had earlier. So this should be compared with, so notice how similar they are. Energy per unit time per unit solid angle is very much the same. No 2 pi. CUP or of time squared. That's what we have been working with. We said then we average over time and all that. But here, what we'll have is, now that I can use those results, so this is 1 over 4 pi times mu naught C over 4 pi times that is an extra factor of 2 pi. Keep it separately purposefully. This is for the solid angle. This is for the frequency. That's a way to keep it separately and remember it. And this is R hat crossed with effective current in the R hat omega, fine, squared. Okay, 20 minutes. So, energy per unit frequency per unit solid angle then is equal to, check this out, or maybe I should write it, A cross B, write it here, right? A cross B squared, which is nothing but A cross B dotted with A cross B, is nothing but A squared, A dotted with A times B dotted with B minus of A dotted with B squared. So this will be I squared minus of R hat dotted with I squared. So that's an identity in because R hat is squared. Right? So if I use that, this will be equal to 4 pi times mu naught C over 4 pi 1 over 2 pi I hat squared. Notice your effective current has an exponential in it. When I take the magnitude of it and square it, it's going to go away. Like exponential oscillatory functions have unit magnitude 1. Right? So that's not going to contribute. This minus ik becomes square of that, so that becomes a k square over 2 pi. So that gives you a k square, which is omega square over c square. Maybe, yeah, in the next step I'll write that as omega square over c square. I would prefer to write that as omega square over c square. And the vector nature of that in the j is square of that j. So this is j of k omega square it and minus of r hat dotted with j and square it again. Okay. This simplification here would be, I went a little fast. Are you guys with me? Okay, so I want to see what this R hat dotted with J is. So let's go and process that. Okay, let's separate calculation here. Remember your current conservation, d by dt, in position and momentum, position and time space is this. Right. Go into the frequency space and the wave number space by doing the prescription. You have minus I omega. When you go into time, derivative of time goes to minus I omega. This becomes k omega plus I times k dotted with j. So k. evaluate this not at any general k, specify that this is omega over c times r hat, that's our understanding. So this becomes I omega rho of k omega equal to I omega over c r hat dotted with j k omega. That tells me that if I cancel out my i's and omega, r hat dotted with j is nothing but c times the charge density. So my, if you allow me to do that, so I'll rewrite this expression there. So energy per unit solid angle per unit frequency is equal to, let me not write k square this time, I'll write omega square over c square, and this is j of k omega magnitude square minus c square of rho okay. What is this space? So this is frequency dependent. If you're doing an antenna problem, you would have a current density like we did for a simple rod, and you will just do that and you will get your radiation out of it. But here we want to do something else, correct? We want to talk about a single point charge going with uniform velocity. So let's have our problem to be just one charge going along a line which is the z-axis. So that's your z-axis. And you have one point charge q moving with velocity v and going uniformly, right? What will be the radiation due to a uniformly moving charge? 0, right? That should not radiate, but still, let's see. But now we are going to come back and say that it's going to go faster than speed of light in the medium. So even though it is going uniform velocity, it should not radiate, but something will happen. That's it. So let's see what that is. So what is charge density in space and time? It's r prime and p prime. Right? For this problem, it will be q times, this is on the z-axis. So that's delta of x prime is equal to 0. Y prime is equal to 0. And z prime is just v times p prime. You're saying that at time t equal to 0, it was at the origin. That's your simple charge density. Current density will be simply velocity times the charge density itself, right? So it is z hat times the velocity, right? Times q delta of x prime, delta of y prime, delta of z prime minus vt prime. But we are interested in the Fourier transform, right? If we want the radiation, frequency dependent for radiation, we should be going into the Fourier transform of this. So Fourier transform this, so rho of k omega, both space and time, right? So will be equal to dt prime, integrate over all times, all space, dq of prime, all space, and this is e raised to minus I omega t prime and plus I, no, this is plus actually, and this is not, should not matter. K dotted with K dotted with R prime. And rho of RT, which is Q of delta of x prime, delta of y prime, yeah, okay, z prime minus vt prime. K here is kx, so notice this quantity here is kx times x prime plus ky times y prime plus kz times z prime. So I'm setting x prime equal to 0, y prime equal to 0, but z prime is not 0, it is b times t prime. Right? So this is equal to, in the root space, so that's minus, oh, there was a q also, q. That's equal to q times time integral of, of exponential of I omega t prime. When e goes to 0, there is a minus kz times z prime is v times t prime. But what is my kz there? K, remember, is your omega over c times r hat. So this is the z component of my r hat. So kz would be equal to omega over c times cosine theta. So this is equal to q times minus infinity to plus infinity dt prime exponential. There is an omega coming from here. There's a t prime in both. So there's an omega, that is t prime times omega, and then there is 1 minus v over c times cosine theta. Okay. Which is equal to q. So I can, yeah, what I mean, so this is q of times delta function. Oh, by the way, yeah, if you're used to checking dimensions, you might suddenly worry. This, what's the dimension of charge density? Charge per unit volume. What's the dimension of this? Exponential doesn't have any dimensions, so this is charge times time. Right? What happened to dimensions? I'm saying this is correct. How can that be correct? Charge density is charge per unit volume. So how can this be correct?
The dimensions got Fourier transform.
Very good, right? This is a Fourier transformed current density, and Fourier transformed so rho of RT, where is, yeah, rho of RT is d cube R, no, d cube K dt d cube omega times exponential of rho of k omega. Right, so charge density, then there is a k also comes in, omega also comes in, and if you take care of all that, that will, let's see this. So this is charge density, right? So q over length cube, k is 1 over length, so this is 1 over length cube, this is 1 over time, and then the charge density of rho of k omega. So there is L cancels at q times t, which is exactly 2 times t. So it works out all the time. Okay. But very immediately when you see that, oh, what happened to my dimension? Right, and panic, which is what I did. What happened to my dimension? Then I did it. So it's pretty cool. Okay, so this is, but this is delta function, correct? Again, right? So this is q times 2 pi times delta function of omega 1 minus v over c cosine theta. Right. So my charge, this is going to be square of this. But when does this function evaluate? Remember, delta function evaluates whenever the argument is equal to 0. When does this become 0? So this becomes 0 whenever either omega is equal to 0, that's static. It's not moving, but our charge is moving, so that's not possible. Or whenever 1 minus b over c times cosine theta is equal to 0. Right? That means b over c times cosine theta is equal to 1. When does that happen? Or what velocity can that happen? It can never happen because velocity v over c is less than 1, cosine theta is less than 1. This can never happen, which is a statement that it never radiates. Unless v gets greater than c, right? Then there is a room there. Right? So let's try that. So how do we take care of that? So before doing that, I need to do it, having clarified that where that radiation is going to come from. So that's a trick, okay? That we can get greater than c in a medium. So that's what we're going to exploit. But before that, let me do a little more processing here. This is rho of k, right? I need rho of k squared. Right? So let's do the rho of k squared. And that requires a little processing in the sense that because there are two delta functions, right? Whenever you have two delta functions, you're in trouble. Why? When you have two delta functions, that is delta of x times delta of x, right? Why do I say that I'm in trouble? Because this evaluates when x equal to 0, right? If I evaluate this delta function, this will become delta of 0. And delta of 0 is not well defined, right? Right at the point, so that's an issue. So whenever you have two delta functions, either you're taking the, like usually the physical interpretation, you're taking the mathematics too much in the extreme. So you have to bring in all the physical reality in there and make it work. So that's what we're going to do. Let's make that. So we want to avoid that coming in. So let's see. So this is q squared. So this is minus infinity to plus infinity dt prime e raised to it prime omega 1 minus b over c cosine theta. Double this, so that is a dt prime. Yeah, I don't have to do it here, but that's okay. Dt double prime. Any, this could be any function. Like it's a more general statement than what I'm doing. Okay. Having 3 minutes, but I'll take probably a lot more than that. Okay. What I want, so there are two integrals in time. I want to change my integral. So this is the physics coming in. You're trying to get around the mathematical trouble that we have here. So what we're going to do is we're going to create or physically talk about two times. One is going to be called a macroscopic time, which is t plus t prime over 2. That's one time we define. And the other time we define is the microscopic time, which is basically time differences, t minus t prime. So there are two times I've introduced here, t prime and t double. Both are integrated out on a disk, right? Minus infinity plus infinity. But I'm introducing a mathematical substitution here, t and t prime. Capital T acts like an average time, t plus t prime over. So which is going to be very large since you're going from minus infinity to plus infinity. That should be thought of as a macroscopic time, but it's just a mathematical substitution if you want. And this is a microscopic time in the sense what are the time differences between two processes. So that's what the microscopic question.
I'm a little confused with the primes. So is
sorry, t prime and t double prime.
Okay.
I'm going to go ahead of. So that should clarify. If I were to put it back in here, t minus t prime. Yes, so this is what this. Then I have dt prime and dt double prime, right? So I'm integrating. So how you would do this is dt d tau will be equal to partial derivative of t with t prime, partial derivative of capital T with t double prime. This is the Jacobian, right? What is the Jacobian? Familiar? Are you guys familiar with Jacobian?
It's forgotten.
Okay. The last day of the class was quiz, right? Yeah, like look up Jacobian, right? What is a Jacobian? So basically, it's the idea that if you have this integral differentials, how do they transform? I made a transformation now. How does my this transform? So this is given by the determinant of this partial derivatives times dt prime dt double prime. Always in any of the partial or integrals, and this determinant is what is called the Jacobian. And in our case, there is this 1 by 2, 1 by 2, right? 1 by 2, 1 by 2, and there is another feature in here. It comes out exactly 1. So let's do that. That's 1 by 2, 1 by 2, 1 minus 1, right? dt prime, dt double prime, and double line means that you have to first take the determinant and then take the magnitude. Right? That's necessary. This double line means that it's a magnitude. So it's minus 1 by 2, minus 1 by 2, so it's 4. Okay, so I can switch over to this macroscopic quantity, go back all the way there, and so my rho k omega square is equal to, these two are exactly the same exponentials. Oh, what did I make a mistake? Oh, what's the mistake here, by the way? When I wrote the magnitude square, I wrote it as 2 of them. This magnitude square, 1 should be complex conjugate. Okay, so this is minus. So when I write that, it is clear that there will be a t prime minus t double prime coming out, which is tau. Right? And dt prime is d tau times d tau. So what I'll get is I will have a dt integral remaining with nothing to work on. It has nothing to operate on, or nothing depends on t square, and there is a q square times delta function of omega 1 minus b over c times cosine theta. So in a very sleazy manner, if you want, I've got rid of this delta function that was going to infinity. It is there still. Notice this is that. So if you ask where did that go away, like how can you get rid of a divergence just by making some substitution? I did not get rid of the divergence. This is the divergence. But now there is a meaning to this divergence. This is the total time that the process is happening in, which is minus in, even if it is whatever the large time you're talking about, I can divide it out and say that there is a meaning, energy per unit time. This has a physical meaning to it. So what you've done is that delta 0, you've given some meaning to that. So that's what you've done. Same thing happens with the current density, except there is a velocity multiplied with this. Okay, I need 10 more minutes at least. Be patient. So we have changed. So this is now 3 of energy. So this is energy per unit time. This is the total long time that we're talking about, macroscopic time, per unit frequency, per unit solid angle. Right. So energy per unit time, basically there is no time dependence in that, the total time that you're dividing out by. So when I integrate with time, that's just t that comes in. And that's equal to 1 over 4 pi mu naught over c times 4 pi. So resistance 1 over 2 pi omega square over c square. Then there is, I replace the same delta function goes in there. There's a charge square. And remember that delta function of a times x is the same as delta of x over a, right? And the magnitude of a. So let's use that. So that's 1 over omega. Magnitude of omega, if you want. And the delta function that shows up. Right? So that's q square I have taken out. First one is velocity square. Second one is c square. And there is delta function of 1 minus v over c cosine theta. Right? Which is 0 in principle if you are going with uniform velocity, because this will never become 1. Maybe process this a little bit more. So this is equal to 1. Oops, this is equal to 1 over 4 pi mu naught c over 4 pi 1 over 2 pi q square. I can get in that over. So one of the frequency goes away. Let me write this as frequency over c square. And there is a charge square. V square over c square minus 1. Oh, I took a c square out, right? So c square cancels out. So this is frequency. So I can take the c square in, and delta function of 1 minus v over c. All this to calculate a quantity that is 0. And this was first time done in 1938, right? I think by the Russian physicist Cherenkov who did this. Okay. How do we now generalize this to a medium? Like, let's go back to a medium. Let's go back to our definition of speed of light. 1 over c square is equal to epsilon naught times mu naught. That's the property of the medium here. If you're, this is vacuum. If I'm in a medium, I'm not going to be going with the speed of light. Instead, I'm going to go with a slower speed of light. Let me call it c prime. It's basically v, but I don't want to use v because this is the velocity of the particle, right? That's the velocity of the actual particle that is going in. So if you allow me c prime, so that means, and this is always less than the speed of light. And that is equal to epsilon, which is usually frequency dependent, and mu times, which is a frequency dependent quantity. Okay. Let's divide this out. Let's divide this by, let's divide this by this, right? So if I divide the two quantities, c square over c prime square is equal to dividing this by this. So this is epsilon omega over epsilon naught and mu of omega over mu naught. Let me take a square root also. This is what is on the left hand side? Ratio of the velocity of the two mediums and yeah, refractive index, right? Which is always greater than 1 is the refractive index, right? So so let me define n of epsilon as epsilon omega over epsilon naught. Very good, right? So that's a refractive index. Good observation. and mu of omega over mu naught. So I'll define my refractive index, which is n, as n epsilon times n mu, if you allow. So the idea, so we have to go from this, which is in vacuum, to a medium which is uniform, which is not vacuum. So my prescription will be the following: wherever I see a C, replace it with, no, first replace it with C over C prime, because the whole calculation goes through with C prime. In that, replace mu naught with mu prime, sorry, mu, right? And is there anything else showing up? No, that's it, right? And after I get there, I convert it back in terms of refractive index. So that means to say, if I want the medium there, what I'll do is take a C, right? Wherever I see a C, I'll go to C prime first, but then C prime is C over N. That's equivalent to C over N. If I replace C with C over N, I effectively get this for a medium. Is that clear? Start from this expression and replace C with C prime, mu naught with mu. That's like doing it in a medium. But after I get C prime, because of this relation, C prime is nothing but C over N. So C prime is equal to C over N. And mu is equal to, where am I? N mu square times mu naught. Right? So effectively, I'm getting, by replacing C to C over N and mu naught going to N mu square times mu naught. Okay? You with me? Sorry about going too little fast, maybe. Okay. But if you do all this, so we have immediately d cube E over dt, almost there. It's equal to 1 over 4 pi. Let me keep this as mu naught C. Everything I'll keep it as old, but I'll provide in a factor, right? Mu naught gets replaced with n mu square. Right, and C gets a n in the denominator, right? So that's all from there. But all this are for exactness. We are interested in the delta function. That's all that's there. Here, right? So 2 pi omega stays as it is. Q square stays as it is. V square over C square. Now C square is V square n square over C square. Minus 1, and the delta function now, it is the important piece, is n times v over c. Now this can contribute. So earlier there was no radiation because this never gets equal, 1 is never equal to this, but since n is larger than 1, this can contribute. Right? So where does it contribute? That's exactly the, and how does it contribute, let's say? So now this can contribute whenever is cosine theta is equal to C over V times 1 over n. This is larger than 1. You wouldn't expect it to be equal to cosine theta, but n is also larger than 1. So if it is dense enough, I can beat this. Right? So there are fast enough particles where that can happen. So how do you expect this radiation to happen if you really had the resolution to see this? Usually these are so tiny things. So if you have a particle moving in, yeah, so if you have a particle moving in with velocity v, I'm drawing this correctly, right? So you have an angle theta, which is decided by this value. So this is a critical value, right? Theta of c. Why is it in the direction of the velocity? Okay. It moves. No, this is not. I'm confused. Cosine theta is, let's say, a small angle decided by C over V. Yeah, let me not clarify that. Okay, I'll try to swindle it. So this is the angle theta, which is equal to cosine inverse of C over V and 1 over M. And only on this cone, notice the whole energy, so there is a radiation. It's not like everywhere you have a radiation. This is only on this cone at a certain moment. At a given moment, it's on a cone. Only at one angle this contributes. And I'm not showing you the velocity, which direction it is. And if I understand this correct, when you have a boat moving in a river, you see a wake behind it. That's exactly this. Like if you have a flight going faster than speed of sound, you have a shock wave. That's exactly this. It's the same equation that governs it. Cosine theta, it's always on a cone. So shock waves are always on a cone. So all the energy is intensely around this point. So it is so high in energy that suddenly if it comes and hits, let's say, a window, it can shatter a window if you're talking about sound waves. This is light, so this is a different scenario altogether, but they are in a cone. But it is hard to see this because they are so tiny, tiny cones, right? But it is usually blue in color. Why is that blue color showing up? This is frequency dependent, linear in frequency. The larger the frequency, larger the radiation. Right? And frequency is larger for blue color than the red color. So when we see it, it is more. And you can do this more. There are more things you can basically integrate with cosine theta. You can actually get how many photons are emitted per unit. You can get an estimate of that, but I will leave that for now. Maybe ask those questions in an exam or something with small time questions I can ask. But I may not, like since I went through so fast, I'll try not to challenge on this. So for the exam, don't worry of Cherenkov radiation, all of that. Okay. And apologies for going too fast. So it's usually done in at least 2 lectures, if not 3. But I think it helps to see the whole thing. Okay, that's all. Thank you for allowing me such long times, and thanks for listening. Yeah, in general.
Thank you.
Thank you.
What can we expect?
What can we?
Expect on the exam.
Oh, what can we? Oh, okay. It's going to be simple. I don't plan to everything from lectures over. Okay. I won't challenge you. I won't go outside lectures. I won't go outside. Homework, how about that? Homework. Just stick to homework. If you want to prepare for it, just look into it. Should be able to reproduce the homework. How about that? That's reasonable. I don't plan to give anything new.
Like comprehensive from beginning to end, or just
Oh, let's say 70% of what we did later, 80% of what we did later, let's say. Okay. So that's making it reasonably precise. But I want to, but there will be a final exam. That's all.
Later meaning after the midterm.
After the midterm, yeah. Right. So it says 60 to, since I said 20%, you have to study anyway. So it doesn't help much. But yeah, if you're going to give it more time, then move time to the later part. But a little bit here and there. But as I go in the past, it will get simpler and simpler. I won't ask anything. My point is simpler means it's conceptually simpler. You've seen the midterm too, right? You guys struggle with midterm. From my perspective, that's simple. And hopefully you guys also think that, oh, we should have known it. But you might struggle with that. When given as an exam problem, it's natural to struggle. But here I want to mostly, I don't plan to test you on those simple things. That's all over. I want you to just test that you've done the homework. Okay, that's all I will be testing. Does that help? Like, just I want to test that you've done the homework, all the homework. That's my purpose. Yeah. So if you want to spend time, it's a only short time, yeah, look into your homework, and more than that if you want lecture notes. That's it. Most probably homework. It will be a challenge for me. I had to pick up the small pieces from the homework. I cannot give a whole problem. So I had to select the small pieces from the homework, which is a consistent in itself. And hopefully that helps. And thanks again for the semester.
This formula
Yes.
on the board, if you have an index that's less than 1, then you would.
Index that's less than 1. Okay. Then you would you're talking about metamaterials. I didn't think about it. Cherenkov radiation for metamaterials. Good point. Good point. I don't know. So you're suggesting that no, it's okay, right? Metamaterials cannot provide Cherenkov radiation because n is less than 1, it won't radiate, right? Only when n is negative, you might have some issue, right? If, like metamaterials has n less than 1 in some small frequency regime. If n is less than 1, then there is no chance of radiation, right? But that's a good thought. I mean, think about it. Yeah, I would say look up. I don't think people have worked on Cherenkov radiation in metamaterials, or yeah, people. I'm always surprised that you think that people have not done it, and then you said, "Oh, people have already done it." But it seems to me that it won't radiate. At least looking at it naively, it doesn't radiate. Metamaterials will not radiate, or particles in metamaterials will not show Cherenkov radiation. But always there is room, right? You have to think out of the box. So I would say it's a good thought. Think about it. So my immediate answer is no, it will not.
Okay.
But don't accept my answer right away. You might lose a pioneer paper.
Okay. Thank you.
Yeah. Okay. Good. Yeah.
Thank you.
Bye, Michael. Yeah.
See you later.
Bye.